So, revisiting the idea of map projections and metadata, here's a little bit more detailed look using the list of projections in ArcGIS, focusing in on the Albers equal area conic. So, when you look at the metadata for that particular projection, it's going to tell you what its name is. The projection is based upon if it has important geometric characteristics. In this case, a false easting, a false northing, so 0 degrees in both cases. A central meridian of negative 96, which means 96 degrees to the west of the prime meridian. Standard parallels of 20 degrees and 60 degrees, both positive. Latitude of origin of 40 degrees, positive. So those are all northern hemisphere lines of latitude, the parallels. The central meridian being negative away from the prime meridian. Linear unit, so the measurement unit is a meter. So this is a projection that's based upon a GCS, North American Datum of 1983. Okay, and so those properties right there are the things that we need to know, or that ArcGIS needs to know, in order to depict the map information properly on the screen. And those pieces of information will travel with your data if you export it into any other program. And so these are what we call map projection parameters. They're the geometric parameters that define what makes this projection work and what makes it unique compared to all of the other map projections. As I note here in the little green box, you can change the parameters to customize a projection. It's fairly easy to do in ArcMap. So if we were to open that up properly, we could change the central meridian, we could change the standard parallels. For example, this is a map projection that's really good for showing North America. Well, what if we wanted to change it so we would focus in on a particular state in the United States, or a particular province in Canada, or a state in Mexico? We could do that. We could just change where the central meridian is, change where the standard parallels and latitude of origin are. We change all those variables, and all of a sudden we've got a map projection that's being better focused on a smaller area. So you can create custom map projections for your study area if you think it's appropriate, or if your supervisor tells you, yeah, this is what I want you to do. Okay, so we're not necessarily locked into the map projections that are built into the system. You can make your own based upon what's already in there. You can create a custom projection, and that's kind of a cool thing to be able to do. Even though we have access to hundreds and thousands of them, you can still customize that if you want. So this concept of the central meridian, again, by convention, the central meridian of or the prime meridian for all maps on the planet's surface that follow the historical development of maps is going to be 0 degrees through the Greenwich Observatory in England. Okay, so that's our prime meridian. That's the central meridian of most global maps. However, if we want to focus in on some other location, we can change that central meridian to wherever we want it to be arbitrarily. So with a map projection that focuses in on North America, we might use negative 100 degrees, which is negative, meaning to the west of the prime meridian, and that becomes the central meridian for our map. So you could take a global data set, and if it was initially centered at 0 degrees of longitude, you could arbitrarily put in any value you want into that projection, create a custom projection that focuses in on the region you're more interested in, wherever that is on the planet, again being a line of longitude. Okay, so X values, in this case X meaning the origin of the map to the right, are positive, they're to the east. X values to the left are negative of wherever that central meridian is, whether it's the prime meridian or not. The reference latitude for most maps is going to be 0 degrees, meaning the equator, the geometrical and mass center of the planet as it spins on its axis. We use y values above the reference latitude are positive to the north. Y values below the reference latitude are negative, whether that's the equator or not. So we can set a reference latitude, if we wanted to focus in again on North America, using a reference latitude of 40 degrees. So that might be our origin on that particular map. And then values positive and negative below that and above that are going to work a little bit differently on that particular map projection. Most of the time, people are going to use as the overall reference latitude. They'll use the equator. It's just the simplest thing. It makes the most sense. And mathematically, it makes a lot of sense to use that as the origin or the reference. So here we see a representation of something we've talked about, the difference between tangency and secant properties of map projections. So on the left, we've got a cylindrical projection, which is tangent at one parallel, one line of longitude, meaning that the surface is in contact with the planetary surface at that line of latitude. And along that parallel or latitude, there's no distortion. That's where we have zero distortion on the map for all different map properties. The further you get away from that line, the more the distortion is going to increase. So over on the right, we have a secant example where the cylinder is in contact with two parallels as it passes through the Earth's surface at two different lines of latitude. And so this is something that we also call a standard parallel or a standard line. And where you ever have that standard line or parallel, there's no distortion along that line, but the distortion increases the further you get away from that line. So by placing two standard lines on the map in this case, we're going to be reducing the amount of distortion that occurs all over the planet. The equatorial zone is going to be experiencing perhaps a little bit more distortion than the single line, but the rest of the planet is going to be less distorted towards the poles. So that might be something that better fits your particular interests. It's something you need to think about when you have a choice of projections. If they're tangent or secant, tangency means having your paper surface actually touching and having zero distortion at one line of longitude or one point location. And here, secant, we're seeing it as two lines, minimizing distortion. Okay. Properties of the false easting and the false northing. What this does is it sets an origin point outside of essentially your study area, so that all of the values for location on your data set are going to be positive. They're going to be positive towards the north, positive towards the east, instead of being negative to the west and negative to the south. So take a look at this diagram. What it's trying to show you is an origin point on a graph, and you can put the origin inside the continent of North America, or you can put it outside of the continent of North America. If it's inside North America, you have positive and negative values in several of those quadrants to describe locations in and around North America. But if we pull that origin point outside of the continent, then everything becomes positive like this. So it's just an arbitrary thing we're doing to keep all of our values positive. Where you most commonly come into this type of a system would be on universal transverse Mercator and state plane systems. And they're designed to have positive values away from an origin, with universal transverse Mercator being the most common one you'll run into. And it is measuring distances in meters from the equator and distances in meters from some arbitrary line of longitude or meridian. such that all of the measurements in the UTM projection are going to be positive values within each zone. And each zone is going to be based upon a different line of longitude that runs outside of it. Okay, just like you see here. So this is something that might help understand why a lot of natural resource people are going to use UTM out of the field. They don't have to try to worry about what the negative values are. Like if they're using degrees, minutes, and seconds, all of your longitude values for North America are going to be negative because they're all to the west of the prime meridian. This gets away from that, and you just have positive values to deal with. And they're all in meters, so it's very easy to calculate distances between locations using that if you have to do it by hand, well, let alone if you have to do it by computer. So every coordinate system, whether it's a geographic coordinate system or a projected coordinate system, has units associated with it that describe distance relationships. So for an unprojected data set with its units being in degrees, minutes, and seconds, we can have another one that splits those down into decimal degrees. So the straight degree and then the fraction of a degree is known as a decimal degree. Well, we can convert those into anything else that we need, and we just need to keep track of what those things are with each projection so we know what we're dealing with. Okay. The projections that you will be commonly using in the exercises in the textbook for the class will be in either state plane coordinate systems, usually in feet, sometimes in meters, or in universal transverse Mercator type systems, which are done in meters. But either way, one of the properties that you need to be aware of, whatever map, projection, or geographic coordinate system that you're using, is what are the units, how is it keeping track of linear distances on the Earth's surface? What unit is that? How much does, how much space does that represent between point locations if you're taking a measurement? And so, again, the system may report values to you, but unless you know what those units are, the values are kind of meaningless. All maps experience distortion. There is no perfect map projection. Let me repeat that. There is no perfect map projection. Every map projection has distortion. Some of them are designed to minimize certain types of distortion. Okay, and again, as we've mentioned before, the names of the maps give you an idea sometimes as to what property they might be preserving over the others. So here are the four main map properties, geometric ones that we deal with. Area, which is commonly called equal area on a map if it's preserving area relationships. Distance or equidistant map projections, they're preserving distance over everything else. The conformal map projection is preserving shape, and an azimuthal map projection is preserving direction. So as we've seen in these different map projections, okay, sometimes those names get combined. We might have an azimuthal equidistant. We might have an azimuthal equal area. You might have those types of things, conformal equal area, conformal equidistant. So watch the names in these properties and understand that every map projection that you have is probably going to be trying to preserve at least one of these properties, sometimes two, over others. And in order to know exactly what those things are, you may need to get into a formal description of the map projection. The map projection properties themselves and the metadata itself may not give you that information. You may need to do some research to figure out what the properties are for your particular map projection and what it's preserving, what it's not preserving. So here, looking at more at some distortions for different map projections. Mercator distorts distance and area, preserves direction and shape. So very good for navigation, not so good for comparing the sizes of different countries to each other, because of where those countries are located in modern times, latitude and longitude wise. The Mercator projection was used historically by the U.S. and by Europe to indicate just how bad an enemy the USSR or the Soviet Union was, because it distorts the size of the Soviet Union immensely in relation to Europe or the United States. So it can be used for propaganda purposes. As you probably already knew, maps get used for lots of different purposes, and that's one of them. But take a look at Antarctica. Antarctica is just incredibly massive and outsized compared to what it actually consumes as far as shape goes on the Earth's surface or area. I mean, it's just not right. Greenland is just not right. Northern Canada and Alaska and the Soviet Union are not correct. They are massively distorted in terms of area relationships. So then on the right, the equidistant conic distorts direction and shape, preserves distance and somewhat area, although you can see again something really strange is happening with Antarctica here. We really get distortion there. Because it's a conic projection, it's going to be focusing in on one continent over the others. In this case, the northern hemisphere, both the continents of North America and Europe and Asia are preserved pretty well. The further you get away from those locations into the southern hemisphere, we see more and more distortion for South America, for Africa, for Australia. It's really looking strange, and Antarctica is just totally bonzo. I mean, this is not a good map projection for focusing in on that area, but pretty good if you were to focus in on either North America or Europe and Northern Asia. It's a pretty good map projection for those zones. A final kind of a projection is something that we call a compromise, where every map projection property is being distorted, but they're kind of, not so bad in relation to each other. The compromise is that we're allowing a certain amount of distortion for everything, but it's minimizing that distortion as much as it can in order to show area, distance, shape, and distances fairly well as we can, given the mathematical properties and geometrical properties of two dimensions and the limitations that we always have in showing two dimensions that are representing a three-dimensional reality. So the Robinson is a really good example of this. The Robinson was used by National Geographic for years and years and years as their standard global map. And now they use something of the Winkle Tripel line, which I don't really like as much. I prefer the Robinson. But it's a really good example of showing this entire planet all at once. It's not perfect, no map projection ever is, but it does a pretty good job of minimizing all the types of distortion to show things relatively well. And that's what this is for. That's what these types of map projections are designed for, is that whole planetary look, trying to minimize as much as possible all the different types of distortion that can occur. The spatial extent of a map is good to know. Gives you an idea of the scale of the map. Here we see two different entries from data sets, one of them showing most of the planet and one of them showing just a portion of the planet. So in each of these gray boxes corresponds with the map shown to its right. So the top one is showing a spatial extent in X and Y coordinates, X and Y values, north and south of the equator and the prime meridian. So the spatial extent to the top or the north of the map is 83 degrees. To the bottom goes all the way to the South Pole at -90. And right and left of the prime meridian goes 180 degrees each direction. So we're seeing the entire planet except for the extreme North Pole. And if you can't guess, the reason why they're not showing the extreme North Pole is because there's nothing up there but ice. In winter, water. In summer, there's no landmass. So we can cut that off and we've still got the whole world. Okay, so the lower uh, map is showing us a particular area in North America, in the United States, with a spatial extent extending from 45 degrees to the north, 42 degrees to the south, negative 96 degrees is the easternmost side, and negative 104 degrees is the westernmost side of that area. So, if you were trying to look at the entire planet all at once, the top one is more appropriate. If you're trying to look at any particular location on the Earth's surface, the top one's appropriate. The bottom one, the spatial extent is very limited. You cannot depict things outside of that extent. So this is a really important property of maps or data that you might receive from some other person or agency or organization. It's a good thing to look at to say, all right, well, what did I actually get? Is it showing me the area that I actually need for my project or my study? And if it's not, then it's data that you shouldn't use, obviously. Okay. And it gives you an idea here. The little box is calling out. It's showing you what the map units are for these different data sets, in that the degree values are being stored as decimal degrees. So that's a way to measure and break up. Rather than degrees, minutes, and seconds, you're looking at decimal degrees, as was introduced in the slide earlier in this set.